Okay, so on the worksheet we have, there are basic statistics. I gave you a set of numbers, and I asked you to find the mean, median, mode, range, minimum, standard deviation. So I've got 14, 15, 10, 13, 14, 17, 12, 14, 19, and 10. I'm going to do the first set. I'm going to leave the second set to you because I just don't want to go through all this twice. But the first thing we have to do for mean, of course, is just add them up. 14 plus 15 is 29, plus 10 is 39, plus 13 is 52, plus 14 is 66, plus 17 is 83, plus 12 is 95, plus 14 is 109, plus 19 is 128, plus 10 is 138. You got to add them all together for the mean. Oh, no, that's a whole set of 10. So we divide by 10, we get a mean of 13.8. For the median, what's our first step we have to do? Put them in order, smallest to largest. So my smallest number is 10, and then I have another 10. What's next? 12 and then 13. 2 14. 3 14s. 15 and 17, 19. That's right. 1, 2. Oh, let's just do this. And I do have 10 of them, so we're good to go. Second step in finding the median is to find the position. And that's n times 0.5. So n here is 10 times 1/2 or 0.5 gives me 5. And since that is a whole number, it's telling us it is between the 5th and 6th number. Well, it's between them. So technically what you would do is you'd add them together. 14 plus 14 divided by 2 is 14. Either way, it's 14. You'd add them together, it'd be 14.5. Mode is the number that appears most often. That is the 14. Now, I said over the last couple of classes, the mean, median, and mode should be, if not exactly the same, really close to the same. That tells us that there's a good chance that this data is normally distributed. 14, because there's 3 14s in there. The mode appears the most often. The max is the largest number, that is 19. And the min, the smallest number, is the 10. Range, I guess I skipped the range, but it makes sense to do the max and the min first, is the largest minus the smallest. 19 minus 10 is 9. That's my range. Standard deviation is going to be a little bit fun. Yeah, there's some sarcasm there. So I'm going to use some technology to assist to speed it up. So I'm going to put my numbers in here. So there's my 10 numbers. We found the mean to be 13.8, but I'm just going to double check it. It is 13.8. So we're going to subtract 13.8 from each number. So what I did there is I just took this number minus 13.8. Rather than typing in 14, I clicked cell A1. So it's going to take that cell. What that allows me to do is I can copy that formula down and it'll do it for each number. So I just subtracted 13.8 from each number. That's where these numbers came from. Does that make sense? What's my next step? Square them. Good. So it equals that number squared. So again, I'm going to, oops, copy it down, and it squares each of them. Once I've squared them, what do I need to do? Find the sum. There's the total of all those added up. What's next? Yeah, divide by n minus 1. So that's going to equal that number. N is 10, so n minus 1 will be 9. So divide by 9. That would be the variance, by the way. Oh, what's going on there? Nope, it's C12 is that cell divided by 9. It's just saying that number divided by 9. And then finally, square root of that number. 2.82 is our standard deviation. So that's the variance. That's the standard deviation. Any questions? So you do the same for number 2. Go through all those steps for the standard deviation, all the other stuff. Number 3 we have not done yet. We're going to come back to that. Going back, number 4 and number 5. So for number 4, we have our bell curve. It says we have a set of numbers with a mean of 240 and a standard deviation of 32. So what goes in the middle here? 240. What's going to go here? 208. Where does that come from? Perfect. 240 minus our standard deviation of 32. What goes here then? 208 minus 32, so 176. And here, 176 minus another 32 is 144. Going this way, what goes here? 272. 240 plus 32 is 272. Here, 272 plus another 32 is 304. And here, plus another 32 is 336. That's all you had to do for number 4 is fill those in. But I am going to put in these here as well. These percents, remember, are standard. They never change. Because we're going to need them down for number 5. Number 5, A is asking what percent of the data will be between 208 and 272. Well, what percent would be between those two? Yeah, we add up 34 and 34 is 68. For B, less than 240. Here's 240. Less than is this way. What's that add up to? Oh, sorry, I skipped one. B is, yes, between 176 and 304. Let me go back to that. 176 and 304 would be that. What's that add up to? So you're 95%. C is less than 240. I was skipping ahead of myself. So here's 240. What percent is less if I go that way? Add those up. Should be exactly 50%. D, what percent is less than 208? So here's 208, less than is this direction. What percent would those be? If I add those 3% up, I get 16%. E, more than 304. Well, here's 304 here. We add up going that way, more than. That comes out to what? 2.5%. F, between 176 and 272. Well, here's 176. Here is 272 right here. So we're looking at that range. If I add those up, that looks to be 81.5. G, more than 208. Here's 208. More than's going this way. Those add up to 84. And finally H, less than 304. Here's 304. Less than goes this way. That should add up to 97.5%. What do you think? Not so bad? Okay. Back to number 3. So this is the one we haven't gone over yet. Making a line graph. So our line graph looks something like that. I got a grid on there for you to help you line things up. What a line graph is across the bottom we're going to put our sample number. And I only took 8 samples. And our length here is measured in thousandths of an inch. So I have to go from 6.5. So we'll go 6, 7, 8. I don't think I have to go to 9, but I will. That should cover everything. So now the first sample is 7. So I put a dot at 7. Second sample is 8. So I put a dot at 8. Third sample, 7.5. Put a dot there. Fourth sample, 7.25, right there. Fifth sample is 8.25. Sixth sample is 6.5, so it's down here. Seventh sample is 8.5. Eighth sample is 7. So then we just connect the dots. So this is statistically called a line graph. In manufacturing, this can be what's called a run chart. And a run chart is used for 2 purposes in manufacturing as far as quality control is concerned. First, a run chart is used to set a baseline. To determine what the process is doing, it's called under control or not. I mean, the phrases are under control or out of control. I mean, the quality assurance system is called statistical process control. You are controlling the process, or you're not really controlling the process. You're making sure the process is under control by tracking the statistics. Now you'll notice, as we go along here, the points do not. If this were a perfect process, these points would line up in a perfect straight line across the graph. They'd all be exactly the same because our machine would produce the parts exactly the same every time, or at least extremely close. Well, processes aren't perfect, so there is this variation in the process.
How do you choose, 6, 7, and 8, and 9?
You mean here?
Yeah.
That just came off the table. It was somebody measured it. They took a sample, they measured it, and that's what they measured. Sample 1, they took it, they measured it, it measured to 7. Sample 2, they grabbed that piece off the line, they measured it, and it measured at 8. So those are all measurements off that table. So there's variation here. It's not a perfect straight line. All those samples are not the same. So what we have to look at is there's something called assignable cause variation. And common cause variation. Common cause is just random variation. Common cause variation is just when the tool goes into the material, sometimes it'll sway off to one side or the other. It's just random variation that is going to happen. Nothing we can do about common cause variation. I mean, we can improve the process to have a better process, but every process is going to have some sort of variation. Common cause variation is a variation that's just part of the process. Assignable cause variation is something that can be found and eliminated. And that's where this run chart comes in. As we're looking at it, we want to make sure the points on this chart are random. Now, looking at this chart, there are actually two things about the data on this chart that if I were a quality assurance technician watching these points be plotted, there are two things about it that would concern me. One of them, probably the most obvious of the two, is if I did have a center line through here. Let's say 7.5 is what I want the parts to be. What's that? Well, I only have one that's at 7.5, but I expect them to be scattered around it. But what I notice is here they're staying relatively close to 7.5. Here they're starting to get further away. So if I have a continuation of this pattern going forward, I'm just going to go in a different color here. If it continues to be farther away like that, I'm going to be concerned because something's going on in my process. I'm getting further and further. There's more and more variation happening. Does that make sense? So the variation is increasing. That would be bad. If the points did something like this, where they calm down and level out, well, then I'm saying, okay, that was fine, because randomly there will be times when the variation will get further away for a while and then come closer back in. The fact that it started doing that would alert me and I would watch it, and if it keeps doing it, then I would try to hunt down the cause of it. If it calms back down and goes back to normal, I'm okay with it. Random variation can happen. The other thing that concerns me about this, I get my extra points out of here. At the end here, I have 1, 2, 3, 4, 5 points in a row that are going up, down, up, down. I can almost predict that the next point's going to go up, can't I? Anytime you get a pattern that is predictable, that means that there is most likely an assignable cause. So even if the distance away from that center line decreases, if the points keep going up and down like that, it's going to concern me because now there is a discernible pattern. So there are several things that would concern you in something like this. If What's going on here that's concerning? We're getting further and further away from the center line, right? Would this be concerning? I'm going to put my center line in here first. If I had a pattern like this. Is there a noticeable pattern there towards the end? They're starting to get closer and closer to the center line here, aren't they? Is that something to concern myself with? A lot of people would say, no, the quality's getting better. That's closer to where we want it to be. So that's nothing to be concerned with. But it is still a predictable pattern, a discernible pattern. So there's still most likely an assignable cost to that. We want to figure out what's causing that to happen, not because we want to eliminate it, but because we want to make sure it keeps happening. The best way to make sure it keeps happening is to know what's causing it. How about here? What's the pattern that I see? Down, up, down, up, down, up, down, up, down, up, down, up. You know, here it was down, down, up, up. You shouldn't be going down, up, alternating back and forth for more than about 7 points in a row is usually what they go off of. Here it's like 9 or 10 points in a row. Down, up, down, up, down, up. That's a pattern. So something appears to be going on in that process that is causing it to be predictably bigger, smaller, bigger, smaller. Is there something going on here that would be concerning? Anybody tell me what it is? Oh, there is. Can anybody tell me what it is? It appears to be getting higher and higher. It's increasing. Two things actually that can alert us. One, several points in a row that are all above the center line. Second, just looking at it, the line appears to be going up, moving up. Then, of course, just the opposite would be true as something is concerning, as if it appeared to be getting smaller and smaller. Again, here, several things going on. First of all, several points in a row that are all below the center line. That's alerting. And the line appears to be going consistently downward. The final thing that can be concerning is if we have a pattern like this. What's happened there? Just took a big jump, didn't it? This pattern's fine here, it's just all of a sudden jumped up. So the question is, what can cause these types of things to happen? Well, this one here is usually caused by operator error. You've got an operator that's just being sloppy. They're slapping the parts into the fixture, not making sure they're tight or whatever. Parts keep getting further and further away from the center line. More and more variation. That's generally what it is. The only other thing that could really happen there, I have seen it very seldom, where you got a machine where like the spindle is wearing out on a mill, and it's really easy for it to get pushed off. It's actually loose, so there's actually play in it, so it slides off the side. But that's extremely rare that any company lets a machine get that worn out.
What about a loose fixture?
A loose fixture would be more likely to give you something like this. I mean, a loose fixture could give you that, but it has to get flopped back and forth, and that is a possibility. But a loose fixture is more likely to give you this, where it gets pushed off to one side, then the next time you load a part, it gets pushed off to the other side, that type of thing, or it rocks back and forth kind of deal. This one here, who knows what happens? That's why you have to search it out and figure out what happened that all of a sudden those points are now getting closer to the center line. Our quality is actually getting better, and who knows why. So that's where you really have to search down and see what is going on in that process that all of a sudden is working better. This one can be caused by a couple of things. Actually, both of these can be caused by a couple of things. The most common one is a tool wearing out. Something happens to the tool. I don't know if it gets hot or whatever, and it loses its hardening, loses its edge, and it just starts eroding away over time. It can cause things to get bigger or smaller depending on what direction it's cutting in. It can also be buildup of chips. If you got small shavings, it consistently something in there that's supposed to be carrying that away from the fixture, and it's not, so chips are consistently getting in there and they're building up over time, getting bigger and bigger, which is also the most common cause of this one, is a chip or something getting in where it doesn't belong. So now when you go to put the part in that fixture, it doesn't fit in tight. Or the fixture itself just gets knocked and moved. It can cause that all of a sudden that jump. And the other way would be if a sudden drop would be the same thing. Something gets in that fixture that either knocks the fixture out of place or is interfering with the part going in the fixture. You could apply it to the stock market. This is designed for quality control and manufacturing. They do use it in the customer service industry. Actually, a lot of in the late 90s, early 2000s, hospitals and clinics started adapting this for their call. A lot of people would call in and they'd complain that nobody answered their call. So they actually started tracking number of calls that went unanswered and how long the person answering the phone stayed on the phone with a customer. They started using this type of system to track that because they had certain standards. The phone was not supposed to ring more than 4 times before it was picked up and things like that.
So the last one, would that be basically the same as, say, like a tool got jammed up and you call it?
Yes. If a tool slipped and got retightened, that could cause that. Or if it got jammed up in, or chipped a tooth, or the tool itself just broke and it's not cutting as deep as it should or whatever. Now this last part, I'm not going to be able to get into great detail because we only got about 10 minutes here. The run chart, these here are called a run chart, by the way. And it's used to establish if you have a good run chart. In other words, if you have a run chart that doesn't have any of these visible patterns in it, then the process is considered to be random or under control. So it's all common cause variation. So that means we can apply SPC to it. If we have any patterns, any of these visible patterns, we cannot use SPC because the process is not considered under control. We have to figure out what's causing those patterns before we can apply a process control, a quality control system to it. So then once we have used that run chart to verify that there are no predictable patterns, then we still use the run chart to keep tracking it because things can go wrong after we started to apply SPC. So that run chart is something that is ongoing. They have computer programs that basically scroll like a stock market ticker. They graph your run chart. And then as new points get added on, as you take more measurements, they add them on to the end, and they just scroll the ones at the beginning off the edge of the chart. So they might display the last 200 points or what, specimens that you've tested or whatever. Now it keeps this information here in case you need to scroll back through it at some time, but it just displays those last however many points you choose to have displayed. So you can see if in the recent history there is a predictable pattern. I mean, most places will test a part, depending on where you're at, they might test a part every 10 minutes. They might test a part once an hour, depending on what their history of quality is and how strict their controls and stuff are. They have to test those parts. Once we have this run chart, we calculate the range and the mean and the standard deviation of the data, of all those points we've collected. And what we do is we use that to establish two different charts. We have what's called a range chart. And the range chart, what happens is, after we've established that SPC can be applied, there is no predictable patterns, we'll actually take a sample of parts. It might be a sample of 5 parts at a time or 10 parts at a time or whatever. That sample will have a range. And that sample will have a mean. Remember that bell curve we talked about and those percentages, right? The big percentage is if you go 3 standard deviations below to 3 standard deviations above, 99.7% of all the data should stay within that range. So our R chart is really just a visual control chart. You have, this is called R bar, that's the mean range there. And you track, okay, I take a sample, here's the range of my sample, here's the range of my next sample, here's the range of my next sample, range of my next sample. I keep taking samples and I measure the range of those samples and I chart it. And all I'm looking for there is that this is staying no predictable patterns in that range. Next is something called the X bar chart. The X bar chart is tracking the mean. X bar is just a symbol for the mean. So we're taking all these samples of 5 or 6 parts or whatever, and we're plotting their mean. Only we're looking at this curve here again, and we're going to go up 1, 2, 3 standard deviations above, 1, 2, 3 standard deviations below, and this is going to be called the UCL. That's called the upper control limit. This down here is going to be called the LCL. That stands for lower control limit. And so then we plot the mean of each of these samples. Now we would expect what percent to stay between these two lines here? That would be between these two lines on this bell curve right here. Remember that was 34% here and 34% here. We would expect 68% of those points to stay within that range. And how about out to here? That would be going out as far as here and here on this curve. We'd expect 95% of those points to be within that range. And then 99.7 to be within these lower and upper control limits. So that saying is we expect literally only about 3 out of 1,000 measurements to go outside of those control limits. So we're plotting the points, and like I said, we expect like 68% of them to be within these first standard deviation marks. They'll pop out every now and then. And we may occasionally get a point that jumps outside of those control limits. Just like we said up above when we saw this pattern here, we're not going to shut down the process yet, but it puts us on alert that we better be watching closely. If we take a part and we measure it and it falls outside one of those control limits, that puts us on alert. In fact, we may not even wait till our next time to take a part and test it is. We might go back and immediately grab another part and test it just to make sure it goes back within those limits. If we take 2 parts in a row that are outside of that control limit, there's a problem we need to look for. We need to go hunt that down. Or if there's more than a couple of parts within a handful that are outside that control limit. So like I said, literally 3 out of 1,000, so about 1 in 333 would be expected to go outside of those control limits. So these are the charts. The range chart and the X bar chart are the ones that allow us to really track the control, the quality of those parts. We expect everything to stay towards the center of this graph. If it gets out, like I said, 68% between here and here, 95% between here and here, and pretty much all of them, 997 out of 1,000 between those upper and lower control limits. I don't expect you to be able to do anything with these charts right now. We just constructed them. I just wanted you to see them and see how the basic statistics fits into them. Many of you at some point in your career will work for a company. The big one out there right now is Six Sigma. In fact, they use this symbol, Six Sigma, looks like that. What's Six Sigma? Sigma is the symbol for standard deviation. And what we have here, here's 1 standard deviation. Here's another standard deviation. 2, 3, 4, 5, 6, right? There are 6 standard deviations between the lower and upper control limit. That's where Six Sigma comes from. Just like when we did the bell curve, we went 1, 2, 3 standard deviations below and 1, 2, 3 standard deviations above the mean. That's a range of 6 standard deviations, 6 sigma. That's what that comes from. Okay, for tonight, I have a quiz on the basic statistics, very similar to this worksheet we did. So I have that quiz that I'm going to send home with you, and that is all we have for tonight. I'm trying to make sure what I'm giving you actually is the quiz here. And is your statistics at the top?
Huh?
It's like 16 years ago that Lady Smith got hit with the tornado.
Yeah, that was actually
Right down Main Street.
Oh no.
Yeah,
They
They took out
like all their.
We did that one in class too.
I don't even know.
That
Took out everything.
it took out McDonald's, it took out the hotel.
Everything on Main Street, like 6 gas stations.
You know, it
Right
sounds
down
it sounds cold, but that was probably one of the best things that ever happened to Ladysmith. Because I mean, a lot of those buildings were extremely run down.
Oh yeah.
They were in rough shape.
Give a little facelift.
Yeah.
Yeah, it gave them.
Made it look nicer. on Main
Face
Street,
off.
yeah.
I mean, they definitely got a better McDonald's.
A lot of money was lost.
Oh yeah, the insurance company had to pay quite a bit.
So guessing didn't reopen the college. I was like, oh yeah,
Hell yeah. Thank you.